Hi, in today's video, I'll be going through ordinary generating functions. And this will help us solve the last problem of our distribution problem where we want to distribute R identical objects into N identical boxes. So, we have covered before in previous videos the other three types of distribution where we go distinct to distinct, identical to distinct, distinct to identical. And now, before we can solve how to do an identical to identical, and before I tell you why it's hard to do distribution from identical to identical boxes, we'll first have to utilize and make known of the fact that ordinary generating functions are what will be commonly used to solve such problems. And so, let's begin with what is ordinary generating functions. OGF basically means that if you get a sequence of numbers, your generating function will be just defined to be the power series where your coefficients are your terms in the sequence, and so the coefficient of x to power r will be the number of ways to distribute whatever number of objects or arrange or however you model your question to the number of boxes. We'll see more examples later on, but the definition of ordinary generating function is that we use the sequence given to create a power series, and then our coefficient will be attributed to that sequence. And so two sequences are equal if each of the terms in the sequence are equal, and hence two generating functions are also only equal for every coefficient of x to power r, their coefficients are equal. With that, we can now do operations on them, such as adding them and doing a product. And they will be how we normally do them in algebraic context. So more definitions and more generalization will be that we know that the binomial theorem is of this form, where it stops after a finite number of terms. For our power series, they want to go infinite, and so there's a generalization that now our power can be any real number. 1 plus x to the power of this real number will be 1 plus nx plus n minus 1 divided by 2 factorial. And this relates back because n choose 1 is n choose 2 is n bracket n minus 1 divided by 2 factorial. And so you carry on. And you can see that if n is a natural number, at one point in this power series, there will be a term where n minus n, and hence every term after that is reduced to 0. And that's why for n, and this helps us get back what we originally have in the original binomial theorem about natural numbers. With this gives us a common ordinary generating function. And so let's take a look at other ordinary generating functions that are very common. One of them will be 1 over 1 minus x to the power n. And this is just equals to 1 plus x squared plus all the way to infinity to the power n. Hence, this term is 1 minus x to the power minus n. And if you do the expansion out, you realize that the minus signs for odd terms will always cancel out. Because this, and the good thing is now we can pull out all the minus signs, and with it will cancel out with this minus sign because it's minus x, and it will leave positive numbers, and so everything becomes a plus again. But now at the top, instead of n bracket n minus 1, you get n bracket n plus 1, and you keep adding on. And now you can see the coefficients is actually the distribution of R identical to n distinct boxes. So you can see how ordinary generating function, while our end goal is to show how it can lead to distributing identical to identical, it can be actually used to solve all our distribution problem and much more. if we can model the question to fit our generating function. And so this distribution of R identical to n distinct boxes has the ordinary generating function given by 1 over 1 minus x to the power n. So common ordinary generating function is if every term before the nth term is 0 and every term after the nth term is also 0 and the nth term is 1, that's just x to the power n. If it's all 1, it's 1 plus all the way, and then we have already seen that's 1 minus x. And now if there's k squared, is 1 minus k squared. Because now you can think of this as your x term, and so you just replace this with 1 minus kx. 1, 2, 3 all the way to r plus 1, well, that is just 1 over 1 minus x squared. And so we have already seen this, and let's just move on to some operations that we can do on generating function. Earlier we seen we can do sum and product, but now let's say we want to generate more generating functions from previous generating function. Well, some cool ones will be, if you want to shift, you want to do a difference between the previous term, the next term, and your previous term, maybe a0, a1 minus a0 all the way, then you just need to multiply by 1 minus x and you can verify that to be true. If you divide by 1 minus x, you add every subsequent term's previous term to it. If you differentiate, you're basically multiplying each of your term by the power. So now it's a1, 2a2, 3a3. If you multiply x to it, you basically shift these things one spacing. So now it's 0, a1, 2a2, 3a3. Integrating will just divide it accordingly. So there are many operations that you can do on ordinary generating functions, and it's actually up to your creativity to manipulate the power functions, power series. So let's take an application of ordinary generating function, which is we want to model how to select objects from a set. Let's say you have a set of n objects, and we want to denote the coefficient as the number of ways to select r elements from this object. Then, like how we did for the binomial, for the multinomial coefficient, if you recall, we treated one of the factors to be the object, and 1 will represent not choosing it, and x will represent choosing the object. And so with n object, you just need to do 1 plus x to the power n, and you can see that it results in what we have in the binomial coefficient, and so because the number of ways of selecting r elements from from a set of n elements is just n choose r, we can see that the terms will coincide with n choose r. Next, if we want to select our objects from multiset, then we just need to write it like how we did for the multinomial theorem, where we do 1 plus x plus all the way to x to the power n minus n power 1, n1. And that's because b1, you can either select one object, 2, or until n1. And then you do this for k times, for the different sizes of the b2s, b3s, all the way bk's. And hence, the coefficient of xr in this generating function is the number of ways of selecting r objects from the multiset given. And if all these n's are infinity, it means it is just distributing r identical objects into n distinct boxes, because you can treat the members that you want to select as the distinct box, and then you can put this r objects into this. And that's just basically our distribution problem type 2. So lastly, we can really see how does this help us solve for distribution problem, and we'll do now use generating functions to solve for the distribution problem 4, which is identical to identical. And that is actually equivalent to the partition of integers. So why is that so? We can imagine we have 4 boxes, and we can have empty boxes. Well, if we want to distribute 4 objects into these 4 boxes such as they are empty, we can put all of them into one here, and this will correspond to partitioning 4 into one partition, or we can distribute them into 2. So we can put them into 3, 1, or 2, 2, and leave 2 boxes empty now. And this will be just corresponding to 3, 1, 2, 2. And so you can see that the partition of an integer n is the number of ways to distribute n identical objects into n identical boxes. And so I've given the definition of partition if you want to read more. But basically, if we want to distribute an integer r into the different sizes, it is basically 1 plus x to the power of that size. So it's x to the power n1 is like choosing none, then choosing the size n1, 2 of the sizes n1, and then so on. And you just multiply them up, and you can get a simpler formula for this AR coefficient. Then that will be the number of ways to partition your integer r into the different sizes. The reason why I go through ordinary generating function first before distributing problem 4 is because in general, the distribution of identical to identical has no step-by-step recurrence relation, no step-by-step method, and the best way to do so is actually to use the ordinary generating function, or you can do a listing. And even with the ordinary generating function, the function itself might not have a closed form formula for the coefficient, and in the end you get back to listing. And so ordinary generating functions allows us to solve such problems in an easier fashion because it allows us to create a more comprehensible look at how we want to partition our integers. Furthermore, another application that you can see online is that when you have multiple conditions, it makes it hard to visualize the distribution, and ordinary OGFs allows us to create an algebraic formulation of our distribution problem and allows us to thus see it in easier manner for us to count it easier. And that is actually the main use of the ordinary generating function. And usually we want to convert algebraic identities to combinatorics proofs. In this case, it converts combinatorics questions into algebraic questions, which makes it easier to manipulate. So you can just pick the way you want to solve a question and go with it. Hence, I'm going through all the distribution problem and teach you how to use ordinary generating functions to solve other problems. I've hoped you have enjoyed this video. Please feel free to like, share and subscribe and watch our other videos. Thank you.